Likewise, if we consider x times log of x and send x to 0, we're going to have to be a little careful. This is a one-sided limit, sending x to 0 from the right. Then what would this be? Well, x is going to 0. Log of x is going to minus infinity. 0 times minus infinity, that's not going to work. Once again, let us put this over a denominator. In this case, we'll move the x to the denominator and call it 1 over x, so that we have a ratio of two functions. In this case, log of x over x to the minus 1. Now, we're going to apply L'Hopital's rule. I'm a little nervous about Taylor expansions here, because both log of x and 1 over x don't seem to have good Taylor expansions at x equals 0. So, applying L'Hopital's rule gives us what? The derivative of log of x is 1 over x. The derivative of 1 over x is minus 1 over x squared. These simplify to minus x. And taking the limit as x goes to 0 from the right, we see that the answer is 0. Now, L'Hopital's rule can also help in evaluating limits at infinity. Consider the limit as x goes to infinity of log of x over square root of x. It's maybe not apparent what that limit is going to be. Log of x and square root of x both become infinite as x goes to infinity, but at what rate? Is there one that is bigger than the other? Well, let's apply L'Hopital's rule. This gives us the limit as x goes to infinity of what? The derivative of log of x is 1 over x. The derivative of x to the 1/2 is 1/2 x to the minus 1/2. This simplifies to twice x to the minus 1/2. As x goes to infinity, this clearly goes to 0. Well, that's the answer, but what does that really mean? A log of x is going to infinity, square root of x is going to infinity, their ratio is going to 0. What that really means is that the square root of x dominates the log of x. It grows much faster than the logarithm does. While it's true that L'Hopital's rule tends to be helpful in evaluating limits at infinity, it's not universally helpful. Sometimes you have to think. Consider the limit as x goes to infinity of the hyperbolic tangent of x. That is, by definition, the limit of the hyperbolic sine over the hyperbolic cosine. Let's apply L'Hopital's rule. Well, this is easy. What's the derivative of sinh? It's cosh. What's the derivative of cosh? It's sinh. And so we get the limit as x goes to infinity of the hyperbolic cotangent of x. I don't know what that is, so let's apply L'Hopital's rule again. The derivative of sinh is cosh, and of cosh is sinh. And unfortunately, we're stuck in a loop, and we'll never get anywhere. But using our collective head, we know the definition for the hyperbolic tangent. What we really care about is the ratio of e to the x minus e to the minus x over e to the x plus e to the minus x. Now let's think about that. Those first terms are big. E to the x gets large very quickly as x goes to infinity, and e to the minus x gets very, very small. Let's ignore it. What would we get? Well, I think you could argue that the limit ought to be 1. How can we make that a little more precise? If we factor out an e to the x, we're left with 1 minus something going to 0 in the numerator and 1 plus something going to 0 in the denominator. Canceling, gives us, easily, this limit. This is a useful way to argue. Consider the limit of x times log of x over log the hyperbolic cosine as x goes to infinity. I'm going to let you do the work to apply L'Hopital's rule and see what we get. What we're going to get winds up looking a little complicated. Fortunately, there's a hyperbolic tangent involved, which allows us to use our previous result to say that the numerator is going to infinity while the denominator goes to 1. What I want you to do is think about how that answer of infinity could be obtained in your head without L'Hopital's rule. Consider the hyperbolic cosine of x. That's really e to the x plus something small, up to a constant of 1/2. Now, if we take the natural log of that, that should look something like x. Not exactly, but it should grow linearly. And so I would argue that x times log of x divided by something that grows like x should give us an infinite limit. That's a foreshadowing of what is to come, where we want to have a language for discussing or controlling growth of functions. This is called Big O, and it's a beautiful language.
L'Hopital's rule, together with Taylor series, form a wonderful set of tools for evaluating limits. In our next lesson, we'll put these tools to use in studying asymptotics or growth rates of functions. Along the way, we'll augment our tools with one more device, that of Big O.